day, I just laugh.
Oh, well, I'd rather not have that information on YouTube, you know?
Can I get the recording when I made you say
Okay. So let's talk about concavity and points of inflection. And today we're also going to be talking about the second derivative test. Okay, so concavity we discussed last class, but it would be good to have a brief review. Okay, a function that opens downward is called concave down. Well, we're not drawing that. So when it opens downward, we say that it's concave down. When it opens upward, it's called concave up.
Why don't we just call it up down? Why would we have to say concave?
I don't have the answer to that.
Is it
Sorry.
because it's like a cave or something?
I don't think it's related to the word cave.
What does it mean?
Or I think maybe a little bit, because cave comes from the word cavity, so there's some relation. Anyways, we determine whether a function is concave down based on whether the second derivative is negative or positive. So when the second derivative, meaning that we take the derivative twice, when it's negative, it's concave down, and when it's positive, it's concave up. And so when a question asks you, what are the intervals upon which this function is concave up or down, we actually do a very similar process as when we try to determine when it's increasing or decreasing. Instead, we're looking at the second derivative. So perhaps we can do a quick example. We went over something very similar last class, right? Let's say we had a function f of x equals x to the fourth minus 4x cubed. Yeah. And let's say the question asks us, which intervals is this function concave up and which intervals is it concave down? Wow, this is too similar to the classwork, but it's okay. Let's find the second derivative. We're going to take the derivative of the function twice. So the first derivative is 4x cubed minus 12x squared. It's just power rule. Then the second derivative is 12x squared minus 24x, if I did that correctly. Okay, and so we're asking ourselves, which intervals of x is this function here positive or negative? Is the second derivative positive or negative? And that will determine what the intervals of concavity up and down are. Okay, so first good step is always to factor as much as possible. And so we have 12x times x minus 2. And then very similar to the previous kinds of questions, we're going to separate our number line into those points that make the second derivative equal to 0. Okay, so our second derivative, 12x times x minus 2, where does this equal 0? It would equal 0 when x is either 0 or positive 2, right? That is because when x is 0 or 2, the function will equal 0. One of the factors will equal 0. Okay. And so that divides the number line into 3 different intervals that we can check each of these intervals for up or down concavity. Any questions about that? Okay, well, we can test each one of those intervals. So maybe first we can test the leftmost interval, so that's negative infinity to 0. And so we can do a test point, right? We can test x equals negative 1, right? So we're just testing a point here within the interval and see what the second derivative is, whether it's positive or negative. Audrey?
Are we going to have to write down our test numbers, or can we just do it in our head?
I'm okay with you doing it in your head. So we would plug in x equals negative 1 into our second derivative, right? Because that's the one we care about, whether it's negative or positive. And so the second derivative when x is equal to negative 1 is going to be 36. You can check that yourself. And so that means that this interval has a positive second derivative. Then we can test the second interval. For this one, we might test x equals positive 1 for this one. And so the second derivative of x equals positive 1 is going to be negative 12. So that's negative. Questions about that? And then the third interval, we might test like x equals 3 or something, and that's going to give us positive 36 again. And so the third interval is also positive. Positivity. So that's all we covered up to in the previous class. Today we're just going to introduce one more new word, and that is the word point of inflection. I might have talked about that last class, right? That's a word that's also used in real life, right? Like an inflection point is a point where a trend changes. Right? You guys have heard that before, right? Maybe.
So one more time?
Like when a trend is changing, it's like
The trade?
a trend. Like something is originally increasing super fast, but then it starts to change, it starts decreasing. It's like an inflection point.
Wouldn't the points of inflection just be the critical numbers where like
They're very similar to critical numbers, but they're not critical numbers themselves because we're looking at this second derivative here, right? But it's the same idea, yeah. So, right, you guys remember analogies? The first derivative is to a critical number as a second derivative is to a point of inflection. All right, so critical number is the first derivative, but point of inflection, we're looking at second derivatives. It's the same idea, except a little different, and I'll explain why. A point of inflection is specifically defined as a point where the second derivative changes sign. So it has to go from either positive to negative or negative to positive. So that's a little different from critical numbers because a point of inflection has to be a point where the second derivative changes sign, meaning that even if it equals 0, even if the second derivative equals 0, that doesn't mean it's a point of inflection. Because we can have, for example, a case where we have, say, these two intervals, and maybe the second derivative goes from negative, and then it briefly becomes 0 right here, but then it goes back to negative. So even though the second derivative is 0 at this point, that's not a point of inflection because it goes from negative, goes up to 0, and then it changes back to negative. So that's not a point of inflection. It has to go from minus to plus or plus to minus. Okay, so make sure you know the definition well. It must change sign. Okay, and not only must it change sign, but the function also has to be defined at that point. And f of x must exist. Okay, so for example, if you had a graph like, it looked like this maybe, technically the concavity does change at this point here, at the vertical asymptote. Sorry, the concavity does not change for this graph. If the graph was like this, right, the concavity does change at this point. It goes from being concave down here to concave up, but this is not a point of inflection because the function doesn't actually exist at this point. There's an asymptote, isn't there? And so that's not considered a point of inflection. So the second derivative must change sign and the function must exist. That will be relevant for part B on the classwork. All right, any questions? Points of inflection?
is that all we're learning?
A little bit more. Any questions? Let me just finish my lecture, and then I'll let you guys do the classwork all in one piece, because the remainder of what I have to say is not that long anyways. So, okay, point of inflection. That was just the new vocab word, right? Most of the concepts we already know from last class. Let me talk about the second derivative test very briefly. And it's a pretty straightforward concept. So the second derivative test basically helps us determine whether a point is a maximum or a minimum. Okay, so previously we were using the first derivative test, right? So previously we were looking at, these maximums and minimums. And in order for it to be a maximum, it has to transition from a positive first derivative to a negative first derivative. And in order for it to be a minimum, it has to transition from a negative first derivative to a positive first derivative. So that was the first derivative test. Okay. Second derivative test is actually a little easier, and that's why we sometimes use it. Okay. Well, what do we notice about the concavity of these two graphs? All right. One is concave down, and the other is concave up, right? So the first graph on top is concave down, and the second graph is concave up. And if you'll notice, you just think about it, right? Every time we have a relative maximum in our graph, for example, on the top, every time we have a relative maximum in our graph, the graph will always be concave down. And whenever we have a graph that has a relative minimum, it's always going to be concave up at that point. Makes sense? And so that's what we call the second derivative test.
Wait, so you could be like, oh, it's coming up, or it's like coming down.
Opening up or opening down. Yes. Okay, so here's the second derivative test. If f prime of x equals 0, and f double prime of x is less than 0, then x is a relative maximum. Okay, so what are the two criteria? First, the slope at that point has to equal 0, so the first derivative must equal 0, and the function has to be concave downwards, meaning that the second derivative is negative. And that tells us that we'll have a relative maximum, right? Pretty straightforward. And then, if f prime of x equals 0, and f double prime of x is greater than 0, meaning the opposite case, then x is a relative minimum. Okay. Makes sense, kind of. All right. The problem is that the second derivative test doesn't always work, and sometimes it's inconclusive. Sometimes it's inconclusive, and the second derivative might equal 0 or might not exist. So if f prime of x equals 0, or perhaps we have a critical number. Let me write it more clearly. If x is a critical number, and the second derivative equals 0 or doesn't exist, then it's inconclusive, and we should maybe try the first derivative test. But the second derivative test can be a useful shortcut that allows us to not do that every time. Any questions? So to reiterate, the second derivative test, we just check to see where our critical points are first. So that'll tell us where our possible maximums and possible minimums are. And then, based on whether the second derivative is positive or negative, we can determine whether that point is a relative maximum or minimum.
Wouldn't it always be positive because it's 0?
What?
Like you said, when you take the second derivative, if it's 0, does that mean it's positive?
No, we're looking at the points where the first derivative is 0, and then checking to see whether the second derivative is negative or positive.
So you plug in, sorry, I'm just confused. You plug in like if I was to do the 6x minus x squared on the over, how would I go about solving that one?
You would first find the critical points, so wherever the first derivative is equal to 0. And then for each of those critical points, you're going to test and see whether the second derivative is positive or negative.
Got it, okay.
Yeah.